So the part of my research that I want to talk to you about today is integrating sensors into tissue models. And one thing that I feel I should point out is that not all sensors are electronic sensors. There are optical sensors, right? There are optical sensors like the ones that we make, where you shine a laser on it, you see what signal you get back, and it tells you something about the chemical and microenvironment that it's in. And that's the type of sensor that we make. And we want to incorporate sensors into tissue models. Why do we want to use tissue models? Well, for lots of diseases, there's not a good animal model. You know, we work with clinicians in cystic fibrosis, and you can make the genetic equivalent of cystic fibrosis in a mouse, but it doesn't have the symptoms, it doesn't have the disease that humans have. So by making tissue models, we can get towards models for testing new therapies, which represent you and I better, right? Because you're human, I'm human, we're not mice. But further than that, we can start to make tissue models which are personalized and which, rather than just representing all humans, represent Andrea or Hjalmar, right? Those are the type of things that we can do as we start moving towards making more advanced and more clever tissue models. And part of making more advanced and more clever tissue models is integrating sensors that tell us what it feels like to be that tissue model, how they respond to therapy, what happens when you treat it with a drug. So we make sensors in our lab which can measure lots of things. They can measure enzyme activity, they can measure redox potential, which tells you about oxidative stress. But the ones that I'm going to tell you about today are all exclusively measuring pH, because pH is really, really simple. It's a really simple thing to understand from a non-expert perspective, but it can tell you a lot about what's happening in a biological system. So this is our dream, that we can get towards complex systems that have lots of different cell types. Like these are epithelial cells, these are fibroblasts, these are endothelial cells, but they incorporate sensors that tell us what's happening in there. And I'm going to show you the type of sensors that we make and show you examples of these kind of things. So the first type of sensors that we make are these little microsensors, microspheres. And they work using Raman spectroscopy. Now, you don't need to understand Raman spectroscopy to understand this talk, right? You'll be relieved to hear. Even those of you who do understand Raman spectroscopy will be relieved to hear that. All you need to know is that we make these smart little sensors, which when you coat them in gold, give you a really, really, really intense Raman signal. And Raman is just a type of chemical analysis where when you shine a laser onto this thing, it'll tell you about what's happening chemically around it. These things are about 10 microns to 20 microns in diameter. We make different sizes, but the important thing is that we're trying to make them about the same size as a cell, so that when we incorporate them into a tissue model, it tells us what it feels like to be a cell in that environment. So these little things, you can see that they are polymer particles coated in gold particles. And the gold particles are the things which are going to give us this really, really strong optical signal. And we can use, here's an interesting type of culture that we've studied. This is an airway liquid interface, which represents what it's like at the surface of your respiratory tract. So this is a layer of cells which have been grown and then matured with tissue culture media underneath them in the basolateral side, but air above them so that they start to generate their own airway surface liquid. And the airway surface liquid is a product of how the cells are working. So by measuring what's happening in that airway surface liquid, we can see how well the cells are feeling. And we can do something simple by just measuring the pH gradient across that layer of cells, and that tells us how good the junctions are between the cells. It tells us about the tight junctions between the cells and how intact that layer is. But beyond that, we can do clever things where, and here's a schematic of how we get these cells, right? You get these cells by taking a little brush, sticking it up someone's nose, and getting the cells from up here, right? So they're stem-like cells. They've got regenerative capacity, and they can turn themselves into all of the types of cells that line your airways. And 5 years ago, you would have probably thought, oh, that looks a bit uncomfortable, sticking a wee brush up your nose. But nobody worries about sticking a brush up their nose anymore. Right? So we can take these, and we can take them from healthy donors, and we can also get them from people with cystic fibrosis. And once we've made these, because we're measuring what's happening in the airway surface liquid, that's telling us about the activity of the protein that goes wrong in cystic fibrosis. That's called cystic fibrosis transmembrane conductance regulator, right? It's a protein that sits in the membrane and helps with the exchange of ions between the inside and the outside. So you can see that in this airway liquid interface culture here, where we're measuring the pH, when we treat it with a drug, we can measure how the culture responds to treatment with the drug, how it reactivates CFTR, because that's the way that people with cystic fibrosis, that's the way that their lives are being changed at the moment by new generations of drugs which help reactivate the cystic fibrosis transmembrane regulator that doesn't work, right? But those drugs don't work for everybody, so we still need to keep working to find ways of screening drugs that do work for everybody. And we can even look at differences between the healthy population and the CF population. We can see real differences in the way that people with CF are able to regulate the pH in their airway surface liquid compared to people who are from the healthy pool of donors. So that's how we can get really crucial information about how these types of cultures are responding to new therapies just by measuring the pH in this liquid. And we can even move to other systems like organoids, which are really great for high throughput screening. You can measure lots and lots of organoids all in one plate really, really quickly and see how they're responding to different therapies. So we can incorporate the sensors so that we can make measurements inside the organoid and outside the organoid and measure the relative metabolic activity of the cells through making the measurement of the pH inside the organoid. But we want to go further as well. We don't just want to make little things that feel like cells. We want to make an environment that cells can grow on, and so that we can make a measurement anywhere that the cells are growing. So we make these membranes with our collaborator Norbert in the School of Engineering. And these are polymer nanofibers. And when we coat the polymer nanofibers in a really thin layer of gold, 30 nanometers thick, we get the same thing as when we're coating those polymer particles with gold nanoparticles. We get a surface which gives us a really, really strong Raman signal. And so we can make these things and coat them in the reporter molecules that tell us about the pH. We can even incorporate them into tissue culture plastics. So these are the types of plastics where we grow our airway liquid interfaces. And we can incorporate our membranes into these plastics so that we can start to move towards doing biological experiments without having to get the biologists to change everything that they use, right? Because people don't want to do that. They don't want to change their whole lab to do a new type of measurement. We want to have the type of measurement that we're making incorporated with the type of plastics that people already use in the lab. So here's what they look like under an electron micrograph. So you can see the polymer fibers there, and these are the cells growing on the polymer fibers. The cells are really happy to be there, right? They've got little microvilli, they're happy sitting there growing on the polymer mesh, and everywhere that one of these fibers crosses another one is a place where we can make a measurement of the pH, which means that's a place where we can measure the local metabolism of the cell. So we can tell the difference between how well this cell is doing to how well that cell is doing. And if we do, for example, a wounding assay, trying to look at regeneration, we can figure out where is the energy being directed in this culture to help this, regenerate and repair. So we think that these types of materials are going to be really, really important in making lots and lots of measurements of how local cells, right down to the single cell level, are behaving in complex cultures. And so to exemplify that, we can treat these cells with a drug and see the difference in the metabolic state by making the measurement right underneath the cell of the local pH. Now, Raman spectroscopies, okay, I hear you. I'm going to skip that, right? But if you want to hear about transplantation, come and talk to me afterwards. I just want to say something about the people in the IRR Chemistry Hub, because it's a very special place where chemists are situated in the same building as people working on biomedical problems. We have a team of PIs, including Matthew Horrocks here, who works a lot on super resolution optical stuff for biomarker detection. Lin-Kong Meng, he's an electrochemist, also looking at biomarker detection and electrochemical imaging. And the co-head of the Chemistry Hub, Mark Vendrell, works on these smart optical probes for studying biological systems. So it's a great place to work. It's a great place if you want to come and collaborate with us to try out some new ideas in a relatively low risk and exciting environment. And I think I should probably stop there, right? Thank you.